All right, we're going to start out by learning what I like to refer to as the computer's native language. That is the basic system by which the computer represents information. Similar, you can think in terms of how we represent language, human language information through our writing. So how does a computer represent information? Well, it uses bits and bytes, and those lead to a more complex system called binary. So let's look at some of these terms and concepts. So here are some terms and concepts you'll want to know. First of all, microtransistors. This is the basic component of a computer. A computer is an electronic instrument. It has a bunch of microtransistors, that is electrical component that can either be on or off. And that's what the computer is. These, a bunch of them, a bunch of microtransistors lined up together next to each other, and they're either on or off. And there's a bunch of them, and so you can do a lot of things with them and represent a lot of information with the configuration of those components, those microtransistors. And the information of whether or not each microtransistor or a string of microtransistors next to each other are on or off is represented in two numbers. One means it's on, zero means it's off. So that information of whether or not the microtransistor is on or off is called a bit. So we're going from the concrete electrical component to an abstract idea of information. So we're using whether something's on or off, which is just electrical current, that's a physical thing, and it's going to represent information. And since we have a bunch of them, we can get fairly complex in what information we can hold. One going on and off doesn't really tell you much, but thousands or billions of them, hundreds of thousands of them do. There's a lot more information that can be held. So a bit is an abstract idea of information. It's a unit of computer information. Behind it is a physical microtransistor, but we won't go into that anymore, the electrical engineering of it. That's as far as we'll go here. Just understand the kind of that bridge from physical thing to an abstract idea of information. And that information, that unit of information is called a bit. So computers store all this information, all its data, whether it's computer code, whether it's text, whether it's images, whether it's sound, as bits, right? So again, electrical components on and off, those are being used to represent information, similar to how a physical symbol, physical element such as ink is wiped onto a piece of paper, and all of a sudden it represents an abstract information, such as this is an A or a B. Oh, and this is a word. So all information in computer is stored in abstract things. They're called bits. And those are kind of like letters in an alphabet, which is a pretty basic information, but usually we don't talk in terms of letters, we talk in terms of words. So that's a bunch of letters put together. In the same way, by parallel in a computer, when you put together bits, you get a byte. And specifically, when you put together 8 bits in a row, that is a byte. So a byte is a unit of information, like a word if you want. It contains 8 bits. So 8 bits in a row make a byte. So for those, again, going down back to the concrete, 8 microtransistors in a row, whether they're on or off, the information is held as 0 or 1. You put those together, you think of them as representing some sort of information, which you can then give to be text, for example, or instructions to the computer. But 1 is not very informative, so we usually think in terms of larger units, more bits, and specifically 8 bits, which is a byte. Okay, a lot of basic information, nothing really hard to understand there. That's really about all we're going to go into it in this class. But there you go. That's pretty much all you need to know to understand a computer's native language, how it represents information. Computers are a lot more simple than human language. Let's think about this for a second. So we are taking a concrete thing of microtransistors being on or off, which is information, which we can then, a bunch of them put together, we can help communicate more complex information. But we're actually underlyingly, the computer's native language is these digits that represent the on or off, zeros or ones. So let's talk a little bit about digits. One thing that I found for myself and for many people is that we have a very tight connection often between this abstract idea of value or amount and these Arabic symbols or these digits, 0 through 9, that we forget that these digits, these ink on paper or black pixels on the screen, are just arbitrary symbols. They don't have any value or amount in and of themselves. And also, our system that we use to count, where after you get up to the 10th digit, which is 9, you start with 0, 9 is the 10th one, you add on another column and you start over with 0 or 1. Well, with 0, but we leave the zeros off, and so you go to a 1, right? And that 1, 0, when you switch over to the column, that represents 10. That's a decimal system because we have 10 digits. Okay, this is what we use. And we use it so much that, again, I've found that for myself and for many people, we don't even think about it. We just take it as natural. We never consider that these are arbitrary symbols, and we never consider the fact that there's no reason why 1 and 0 should represent 10. And there's no really good reason why we should use a system that uses 10 unique digits, 0 through 9, and goes based on 10. Or is there? Well, when I ask this question to people in person, it usually takes a little bit, but usually after a little while, I'll see people raise up both their hands. Why do they raise up both their hands? Because on your hands are 10 fingers. And if you think about how we count, the simplest way, we start at very young, and how you're going to count something is we use our 10 fingers. So that actually seems, well, the theory is actually that this isn't totally arbitrary, but that it's natural for people to count in tens because we have 10 fingers. But it's actually uh, more connected to our brains than even that, than the fact that we have 10 fingers. Okay, so there's Arabic digits and there's 10 digits. We actually have this base 10, this decimal system reflected in our language, in a lot of language. And English is kind of a weird example, but if you think about it, we have unique words for the numbers starting with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All of them are unique. Actually, 0 was added, so we actually got 11 digits there. But when we get to 10, up to 10, we have unique words for them. And then I said English is a little weird because we also have a unique word for 11 and a unique word for, almost unique word for 12. But after that, which is interesting, we even have a special word for dozen. I don't know of another language that has that. If you can figure out why English is special in that way, the history of it, let me know. Send me an email. I'd love to know about it. But after that, after 12, we start seeing clear repetitions. So 13, that's the 3, the thir, that comes from 3, and the teen, that's 10. So we're really saying 3 and 10. And then 14, same thing, 4, teen, 4, 10. 15, 16, 17, 18, 19. Now we've hit to our second group of 10. We've just covered it. We're going into actually the third group of 10. But we've covered 2 total groups of 10. And so we switch to the next number and we go 20. And if you hear it, you won't hear the connection, but if you see it written, our history has preserved the connection in writing because there's a TW in 20, just like there's a TW in 2, even though they're not pronounced the same. And then the T, twin T. So it is actually twin, that comes from 2, and the T there is 10. So it's actually 2 tens, right? And then 21, 2 tens and 1, 22, 2 tens and 2, 23, 2 tens and 3, and so on and so forth until we get to 30. And that's the same thing, 3, 10, 30, 3, 10. And this goes all the way up to 100 and beyond. It just repeats always in these groups of tens in our language. So you can see in the language, the way that we construct our language represents this 10 idea. And the theory again is because we have 10 fingers and that seems like a natural way to count. And this is actually held up, the theory is held up because the most common system of way people count in their language with those unique or repeating sounds and parts of words is a base 10 symbol. Beyond that, the second most common way in language that you'll see, the second most common system where you'll start seeing the repeating of the sounds of words and parts of words, well, the first common is 10, The second most common, you might guess, if you think about 10 fingers and then you take off your shoes, and what do you have? Another 10 digits, our toes. And so, sure enough, in languages, if you speak French, you know this, the second most common system in language, reflected in our language, is the 20 base system, where you have unique numbers, maybe up to 20, and then you start repeating, and you get to 30, and it's 20 plus 10, and then 40 is two 20s. This is actually the second most common. So, this arbitrariness of the decimal system is not totally arbitrary, as best we can hypothesize. The Arabic digits we happen to use to represent that, and the column system that we use with the one and the zeros and the repeating columns that grow, this is arbitrary. And it's a really cool system. I'll cover that in another video, but for now, you can see the connection here between numbers and language, which we're going to cover a lot in this class. So this is kind of an introduction to that. It's really cool. All right, so bits, binary. Wanted to cover a little bit about digits because now we're going to go, sorry, bits, bytes. Let's talk about digits because now we're going to talk about binary numbering systems. So I just covered some of the basic logic and the linguistic connections to the decimal system and then the 20 base system. But in computers, there's not 10 unique digits, there's not 20 unique digits, there's only 2 unique digits. And so the system here is the binary system. It's a system of numbering using Arabic digits. It comes from the word binary, which means which means two. So two parts, similar to bicycle is a cycle with two wheels, and so on and so forth. But they use the same digits, so this can be confusing. And again, you have to separate this idea that those Arabic digits, as you see them written, just automatically mean values. There's a whole system here, which again, I'll cover in another video. But the basic idea I want you to get here is that just because you see a string of Arabic digits, like ones and zeros, does not automatically mean that it's using the decimal system, right? Just like if you see letters, Latin letters like A, B, C, D, E, F, G, together in some combination, it does not automatically mean that that's English. It could be the same symbols being used in a different language, so a different system. And the same thing with our Arabic digits doesn't automatically mean that the first column all the way there on the right represents how many ones, and the second column is how many tens, and the third column is how many hundreds, and all the way up to the eighth one at the left there, that one, which tells you how many tens of millions, right? So this string of 8 digits with the 1 at the beginning, in the decimal system, it says that there is a total of 10 millions. And all the other columns are 0, so it's 10 million. That's what it represents. But you take those same string of digits down there at the bottom in binary, because the system is different, we're not counting with tens, we're counting exponentially by twos. So decimal system counts exponentially by tens for each column, binary with 2, exponentially by 2. So the first column is not how many tens, but how many ones. The second column, double that exponentially. How many twos? And then exponentially, 2 times 2. The third column from the right is how many fours. Get all the way to the left where that 1 is, in the 8th column from the left, and you follow the math through, and what it's telling you is how many 128ths there are. This seems unnatural if you've never run into it, but with binary, it's a simple, natural thing. So 8 digits in a row with 1 in that left-hand column. In decimal, it's 10 million. In binary, it's 128. Okay, so the basic idea here to cover is that you can use the same digits. They're arbitrary, they're Arabic digits. If you know the system, then you know what the value or amount is that those digits represent, but you have to know the system. You can't automatically assume that it's a decimal system. It could be a binary, it could be something else. It could be a hexadecimal system, it could be a base 20 system.